Okay, so what I want to do now is to do a little calculation just to show you that everything hangs together. I'm going to calculate the energy flux in an electromagnetic wave using stuff that we learned a long time ago, namely how much energy density is there in an electric field or a magnetic field. And what we should get from that is the same thing that we got in the immediately previous video from the Poynting vector. So let's just go ahead and do it. So I have an electromagnetic wave traveling in this direction. It's going in the x direction, moving at the speed of light c. And I'm going to consider this cylinder. And this cylinder has some energy density, some energy in it, du. And how long is this cylinder? Well, the length of this cylinder is c times dt. What that means is, if I ask what is the rate of energy flow per unit area in this electromagnetic wave, well, what is it? Well, it's given by du dt, because in a time dt, this much energy goes through this cross-sectional area here. So this cross-sectional area here, area A, and so I have to divide, if I want the rate per unit area, I have to divide by A. So the rate of energy carried by this electromagnetic wave through this piece of cross-sectional area per unit area, well, that will be the amount of energy in this cylinder, which is c dt long, because in a time dt, it's this much energy that's going to go through this piece of area. So I need to figure out what this du is. How much energy is there in this cylinder? And then I'll have the answer. The rate of energy flow per unit area in the electromagnetic wave. Actually, instead of saying in the electromagnetic wave, I'll say carried by the electromagnetic wave. So the rate of energy flow per unit area carried by the electromagnetic wave. I've got this piece of area here. How much energy is flowing through it per unit time? That's what rate means. So it's energy per unit time. That's du divided by dt, this much energy per time dt, and divide by the area. And now I just need to work out, actually I have everything I need, I just need to work out what du is. So I need to work out what du is. And, well, du is going to be an energy density times a volume. So the energy density is going to go here. What's the volume? Well, the volume is the length of the cylinder, c dt, times the area. So the length of the cylinder is c dt times the area. And now what's the energy density? Well, the energy density is the energy density lowercase u in the electric fields plus the energy density in the magnetic fields. And if I use results from much earlier in 802, that gives me 1/2 epsilon naught times E squared plus 1/2 B squared divided by mu naught times C dt times the area A. So this is my du. I have some electric and magnetic fields in here. Their energy density goes like E squared for the electric energy density, B squared for the magnetic energy density. So the total amount of energy in this cylinder is energy density times volume of the cylinder. And now I need to evaluate what I actually want, which is du dt. And when I do du dt, this dt is going to cancel. Divide by A. When I divide by A, this A is going to cancel. And so the actual thing that I want, the only thing that sticks around from over here is this C. So I have a factor of C. And then I have 1/2 epsilon naught E squared plus 1 over 2 mu naught times B squared. And that's my answer. Except it doesn't quite look like the Poynting vector yet. But now I need to work on it a little bit. In the electromagnetic wave solution that we found by solving Maxwell's equations, E was given by B naught times C. Or E was given by B times C, or B was given by E over C. And so we can use that. Let's use that. So first of all, I notice that I have a common factor of a half. So let me write C over 2. And then here I have epsilon naught E squared. Well, I'm going to write one of those E's as B times C. And so that's going to give me epsilon naught times C times EB. And here I'm going to write one of those B's as E over C. So that's going to give me plus. So I write one of my B's as E over C. And that gives me EB over mu naught C. So now I notice that I have an EB in both. So I'm just going to write the EB out front. And I'm going to choose to write EB divided by 2, and I'm going to put a mu naught here. Why am I going to put a mu naught there? Well, it's because I know where I'm going. The Poynting vector was EB. When E and B were perpendicular, which they were in our solution, it was E cross B, but E and B are perpendicular, so that's just EB, because E and B are perpendicular. So in our solution, E cross B is EB, and the Poynting vector was E cross B over mu naught. So I'm going to put a 1 over mu naught downstairs. And then I'm going to see what I have left. And I've kept this 2 along for the ride. So I need a 1 over mu naught. So from this term, I'm going to get mu naught epsilon naught C, and there's a C there. So that's mu naught epsilon naught C squared. Mu naught epsilon, that rings a bell. I'll have to figure out what that is in just a second. Now here I've written the 1 over mu naught outside. This C cancels this C, and so all I have from that is plus 1. And now I realize why this rings a bell. The reason this rings a bell is that C squared is just 1 over mu naught epsilon naught. Look at that. C squared is 1 over mu naught epsilon naught, so this is just 1. And so what I have left is EB over 2 mu naught times 1 plus 1, which is to say I have EB over mu naught, which is indeed the magnitude of the Poynting vector in this electromagnetic wave. So I've just convinced you that if I ask how much energy is in this cylinder, therefore how much energy flux is there going through this area, and derive the answer to that using things we learned a long time ago, much earlier in 802, what we get is exactly the magnitude of the Poynting vector for the solution to the electromagnetic wave. I want to make sure, though, that you understand that going into this calculation, there were things that I did not explicitly write on the board. This calculation only works if E and B, only works the way I did it if E and B are perpendicular. It only works if E is B times C. And those are features of the particular solution to Maxwell's equations that describe a propagating wave, which we derived earlier. So I've pulled in this little calculation, I've pulled together things from electrostatics, the energy density in an electric field, magnetostatics, the energy density in a magnetic field, and the specific characteristics of the solution to the full Maxwell's equations in vacuum that describes a propagating wave, and shown you that everything ties together, and the energy density per unit area carried by the wave is indeed the Poynting flux as it had to be.